afraid that what I want to say, actually I wasn't really sure what this round table was going to be about, what the topic would be. But what I thought would be most useful to say would be just to say a few fairly general words about issues in quantum mechanics. Much of the discussion this morning was concerned to quantum mechanics, although not so much about the interpretation of quantum mechanics, but it was there. What I want to say is, talk about is just a way of making, I think, a useful classification of possible versions or interpretations of quantum mechanics. Rather coarse, but it would be good to get it on the table. And the classification, of course, is going to be concerned about what's real in quantum theory, which is often kind of vague. And I want to focus on the most important object, I would say, the least mathematical object in quantum theory, the wave function. Probably you should think about maybe the wave function of the universe. That's what I would prefer to think about. And this is certainly an audience in which I guess most people wouldn't object. In many physics audiences, people are upset about talking about the wave function of the universe or as the universe, or just in general, the universe as a whole. And the real issue that I want to use for the taxonomy of versions of quantum theory is based on one's attitude towards the wave function. If you don't like to think about the wave function of the universe, think about the wave function, your favorite wave function, the wave function of a system, or just the wave function of quantum mechanics, however you think about it. There are, I would say, three possibilities concerning the wave function of the universe that I want to focus on. One possibility, and these are all concerned with the reality of the wave function of the universe, or the wave function of quantum mechanics. Is it something real, or is it something not real, merely subjective, merely like a probability distribution, reflecting ignorance, not objective? So the first possibility is that the wave function psi is something. No, let me think, not psi is something. Psi is everything. So if psi is everything, it's presumably real, and it's all there is. All facts of the matter in the universe have to be in the wave function. The second possibility is that psi is something, but not everything. So there's the wave function of the universe, but there are other things in addition to the wave function. The wave function does not exhaust all the facts, all the realities that there are, all the material that there is. And the third possibility is that psi is nothing. It's merely subjective. It's not part of the furniture of the world in any sense, even in the sense of being sort of a law. The law is objective. It's just a tool for calculation in the same way that a probability distribution, it doesn't correspond to any true facts, just to ignorance. Now, I would say these are the basic possibilities about the wave function, and I would think that if anyone is presenting his own version of quantum mechanics, one thing, you probably have noticed that when you read about versions of quantum mechanics that are not your own, you have the thing you prefer, you often have a lot of trouble understanding what exactly was being proposed. I think one thing that would help is if in that proposal the person made clear which of these three possibilities their proposal corresponds to. Now, it sounds like these are the only possibilities, but the situation is a bit tricky. First of all, there are certainly many, many people, physicists, who say psi is everything, and that has a certain appeal. There are many, many physicists who say psi is nothing. And that has a certain appeal because it's a very weird kind of thing to take seriously as part of reality. Much more striking is the fact that it's often one and the same physicist who holds both of those views. Which presumably it corresponds to the view that nothing is real. It is an obvious fact the way I've ordered things here, and by the very meaning of the things that I've listed here, that the most modest position is psi is something but not everything. I'm not saying that as an argument in favor of the middle position, because one can think of arguments in favor of all the possibilities here. And my point here is not to argue about what the best possibility is. What I would like to indicate now is my sense of how some of the most prominent versions or interpretations of quantum mechanics fit according to this classification. I should also have said, by the way, that I am sure there would be people who say none of the above. If somebody proposes a theory, a version of quantum mechanics, an interpretation of quantum mechanics, that he's not happy with this classification, he should then clearly say, no, none of the above, and then explain how that could be so. That would help in understanding the point of view. So here are the most famous, of course, possibility for the psi is everything view is, of course, Everett. Many worlds. And I think I need say no more about that. I think everyone would agree about that. Not that it's the best view, but it's the characteristic, the basic view corresponding to psi being everything. Another possibility, I should put it in parentheses here, is spontaneous localization, GRW, collapse theories. In collapse theories, psi is everything. It's in parentheses for two reasons. One, because it's a theory in which the wave function is not the usual wave function, and in collapse theories, the wave function does not evolve always according to Schrodinger's equation. So maybe we're not talking there about the same psi. And there are other reasons for qualifying that, which I won't go into now. Now, the psi is something, I suppose the most famous possibility there is Bohm, de Broglie-Bohm, Bohmian mechanics, pilot wave theory. They're all the same thing. And there, in addition to the wave function in the simplest case of non-relativistic quantum mechanics, you have actual particles with actual positions following trajectories guided according to a simple equation of motion. But I believe it's also the case that in this for the second possibility, we have decoherent histories, where you also have more than the wave function of the universe. You have, in addition to that, histories of whatever properties, observables you're interested in. Probably the most important observables are fundamental observables, which Jim would like to distinguish, and I would too. In non-relativistic quantum mechanics, given by positions of particles. The difference between decoherent histories and Bohmian mechanics is simply a difference of what law you give for the histories. But the histories themselves are not histories of the wave function. I would also put, by the way, causal set theory and maybe some other things in this middle category. I'm sure I'm leaving some stuff out. Now, in terms of the last category here, I guess I would conclude quantum Bayesianism. The quantum Bayesians seem to want to get rid of the wave function and say that's not real. I'm not sure what they regard as real. And let me just say one more thing. I guess my understanding of Copenhagen is also kind of like psi is not everything. In addition to the wave function, there are macroscopic variables which change value according to the wave function. Done.
Thank you very much. Carlo.
I'm a bit amazed because I had prepared some notes, and this is exactly the notes I prepared. So, Oh, really? I'm not joking. You can check. But before getting to that, I thought that my job was to make a little comment on what was said previously. So I want to make just two remarks about what we heard this morning. First is a bit critical about the ideas I heard, and the second is supportive to some of the ideas I heard. So the critical one regards infinity. And I want to just make a warning, sort of, I think it's required after what we heard, with two small examples. And this is, the first one is a sort of mistake that humanity made in the past. If you measure the average curvature of the ground of your floor, of your city, of your region, then the average curvature is very small, right? So it's very narrowly, the experimental value is very close to 0 for the curvature, from which you obviously infer that the Earth is flat, it is infinity, right? Can I get the next slide? Can I get next slide? Thank you. My planet is flat and infinite. I can do it myself. Right, Bruna? Thank you. So second example, we all study statistical mechanics. We all went to classes where we learned that we do understand phase transitions very well, statistical mechanics, and there's a theorem in statistical mechanics that there's no phase transition unless you go to the thermodynamical limit. So if you have molecules, the phase transition only happens in the limit when n is equal to infinity. We all study that. In fact, there's no phase transition for finite n. Okay? So therefore, you can look at a glass with ice, and there's clearly a phase transition here because there's ice and water together, which are two, okay? Therefore, rigorously, you conclude that there's an infinite number of molecules here. Okay? Now, there's obviously a mistake in both examples here. I think that this mistake has been repeated over and over and over again. Okay? We have evidence that the curvature, the three-dimensional curvature of the spatial metric of the universe is small, which means that the actual universe size is presumably bigger than the habitable, the visible. If you go into the actual numbers, it turns out, which is at least 10 times bigger. There's nothing to do with the universe being infinite. Nothing. Okay? This has nothing to do with the number of molecules being infinite. Okay? So do not confuse infinite as a useful approximation to many with actual infinity. I mean, the distinction between different kinds of infinities, our civilization knows it since quite some time, right? 25 centuries or whatever. Why are we still making this mistake? So I close this parenthesis, and I come to the second observation about what I heard this morning. And I heard about observers, the role of the observers. And here my comment, on the other hand, is in the opposite direction. I think this is a very useful reminder for whatever we do. Because physics has gone over and over and over through this game of trying to disentangle, stop making mistakes about what depends on the observer and what depends on the observed system. We see the sky rotate, okay? So two things. Either this is a property of the sky, okay, the ensemble of the stars and the galaxy, which happens to rotate. We have to need a cosmology which rotates a lot. Or there's another possibility. The sky is just there and we are rotating, right? And it turns out that that's much better manner of understanding what is going on. We divide, we see past and future. Either the events of the universe are by themselves divided in past and future. It's a sort of property of an event to be past or future, or past and future are actually depending on, one point in Minkowski space. I'm just thinking about special relativity. So some things are future with respect to a point, something are past with respect to a point in space-time, and some points are neither future nor past with respect to. And of course, we understood this, that this is a much more useful way of doing this. This means, and I could, we could go many examples like that. So in physics, there is a large progress that have always been made by recognizing how it's not obvious to distinguish property of an object, property of an object which are relative to me. And we use in our language an enormous number of terms which depend on me, right? Indexical term. Here, now, Foreigner, etc., 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 which have a different meaning depending who and when and where and how. So a lot of things in the world can be indexical in that sense. And now we come to this to this point that Shelley illustrated, and I want to take this lesson, which in my opinion is a deep and important lesson, especially in cosmology. Be careful that it's very easy to confuse the first and the third person perspective that we heard this morning in both directions, right? I think the values refer to us, not to the universe, for instance. So with this in mind, I want to come to this distinction. I think this is I subscribe 100%, Shelley, to what you said. And in fact, it's very nice, because I think that here they're representative of these three possible ways of understanding quantum theory. I have always thought that you would like the second one particularly, or at least I have identified you with the second one strongly, and I've always identified David with the first one. I identify myself with the third one very strongly. So I would put relational quantum mechanics here, which is my preferred interpretation, RQM, relational quantum theory here.
I thought you might go there, but I really wasn't sure.
Please be sure, I will definitely go here. So I think that the lesson that a lot of our way of talking about the world is indexical depend on us. It's crucial, by the way, Jenan is here. Jenan wrote nice books around this notion and this idea, from which I learned enormously. Can I get the next slide? I just have a one-line. Sorry, it's me. I have a one-line summary of the way I like to think about quantum mechanics, which I don't want. I don't want. Yes, I do want to make publicity to it now, but I think it's a possible alternative to the way David looks at quantum mechanics, which is a wave function. It's a wave function, and then he writes books to try to explain how, from this wave function, actually the world as we see it could emerge and makes reasonable just be there. I tend to think that this is sort of a misreading of class 1 in quantum mechanics, in which we are told that there's a Schrödinger equation, you solve everything into that. I don't think that's quantum mechanics. Quantum mechanics is the one in the books of Dirac, and the first paper by Heisenberg. Quantum mechanics is about facts, which are nothing to do with psi. So psi, I would just forget about it. Psi is like the action, the solution of the Hamilton-Jacobi equation. It's a calculation device. Quantum mechanics is about facts. Facts are facts, right? However, we know all the difficulties that this simple-minded reading of quantum mechanics. So I think the quantum mechanics about this pen being here, this being here, the electron hitting here, electron being in a point at some time. But we can use this ontology if we want to be realist. Right? This is all under the assumption that we want some kind of realism. If we want to have this sort of realism, we have first of all to relax the amount of the electron is here and here, but not everywhere in between. It doesn't have a trajectory. We know that we don't want it. You do want it, but I don't want to associate a trajectory to an electron. And this works only provided that we understand the indexical nature of the facts themselves. So the facts themselves are actual, relatively to the physical system they affect. This is the relation of quantum mechanics. I think it is consistent. It uses heavily the notion of observable, but observable is not anything, it's not a mind, a psychology, something record. It's observable in the same sense of special relativity or Galileo relativity. This is a speed with respect to the pen. The pen doesn't need to be particularly intelligent to be an observable, with respect to which speed is a relational quantity. I think that facts are relational in this sense, and I think that this is a possible third manner of thinking quantum mechanics, which I personally like a lot.
So I don't think I massively disagree here. I might have some slight reservations, but I think I'll stick to my remit and talk instead just about a couple of thoughts that came up during this morning's talk. So the first is about these questions of probability measures in large or infinite universes, or in situations where there's a multiplicity of observers potentially present. And I don't really have anything very conclusive to say, which I think probably violates my philosopher's charter requirements, but I've just got an observation that I'm always kind of surprised and interested doesn't seem to play more of a role in some of these discussions. And the observation is this. We often engage with these issues by saying something like, well, we're led by our physics to think that we have an extremely large or indeed infinite universe, and furthermore, that we're led by our physics to say that it's got enough variety in it that there should be a multiplicity of observers present, and so now we have a problem, given that single way things are with all these multitude of observers, how do we apportion our probabilities across them? But of course, the reason we have all of that variety in the way our cosmos is laid out is because there have been a whole bunch of individually random quantum mechanical processes going on that have led us to that variety. You know, I think a classical Friedman-Walker, a classical exact Friedman-Robertson-Walker universe has no variety in it at all. It can be as big as you like, and it's got no observers and no problems of this kind. Why do we think that the universe we actually live in has got this kind of variety? We think it because we think it's had a whole bunch of structure formation, galaxy formation, star formation, planet formation, goings on. We think we're allowed to put certain probability distributions on a, per Hubble volume, per megaparsec cube volume over that. Then since we play that out over a very large or infinite number of copies of those volumes, we're going to get a very large or infinite number of observables. And that all sounds fine, but it's interesting that having helped ourselves to a probability measure defined in terms of stochastic dynamics or quantum mechanical probability, or however you want to think about ordinary parochial in this room probabilities, that probability measure then that probability then seems to more or less fall by the wayside, and we find ourselves separately addressing the problem of how it is that we can assign epistemic probabilities to the large number of observers in the single given universe. And I think that's curious. I don't think I've got anything conclusive to say as to what we might draw from that, but I think it's interesting that that's going on. We've actually got two notions of probability in play here, and it feels as if maybe they ought to be a little more intertwined than they can sometimes seem to be in the way these discussions go. Okay, so that's the first thought. And the second thought actually picks up on some of what Don Page was saying about elegance and the bestness of the universe, and it leads to a sort of slightly more general thought. My narrow thought listening to Don's presentation was something like this. The dialectic of understanding it is something like, well, supposing that we want to go for the simplest possible universe isn't going to work, it gets the data wrong, what else could we try? Let's try the best possible universe. Now we've got a problem, because while the universe might be plausibly maximally elegant, it doesn't seem to be maximally good in other respects. How do we resolve that? And then we have an argument leading us to various theistic possibilities. But the immediate thought I have here is that if what we're looking for is a principle other than simplicity to pick out the world, and if our principle, if our stab at that principle, which is how about it the world is best, runs into the problem that the world appears to be most elegant but not actually best, then the kind of cut out the middleman route just seems to be to say, let's just have a principle that the universe is maximally elegant and just run with that.
But it's not, because if zero, nothing exists would be simpler.
Oh, that doesn't sound very elegant, though.
Okay.
Sounds quite boring. This isn't the point. I mean,
This is why this idea of variety as well as simplicity.
Yeah. But the reason I mention that is not really to dwell on that particular argument, but to sort of suggest it's an interesting case study for a sort of more general question about how we run these, some of these anthropic arguments, which have been a sort of theme of a lot of the sort of nascent philosophy of cosmology. And the thought's something like this. We find ourselves often led to an observation that the universe seems to have features in it that don't seem very explicable directly, except that we observe that they seem to be awfully connected to the fact that there is life or sentience or intelligence or the Simpsons or whatever particular feature we think is striking. And that tends to catch us off guard and bother us because the general trajectory of physics and science since the Renaissance has seemed to be that we are eliminating sort of direct appeal to the high level, direct appeal to the purposeful or the aesthetic or the complicated or whatever, and we want an explanation which brings these things out and doesn't put them in at the base level. So we could imagine saying, okay, let's just put them in at the base level. Let's say, okay, we need to have as an assumption in our physics that the universe is life conducive as an axiom. And we don't like that very much, so we say, what else can we do about it? But I think if any given thing we want to do about it is postulated only so as to reproduce that result and has no evidential support other than reproducing that result, it doesn't seem to me epistemically it improves in that result. So for instance, if our reason for thinking that we live in a multiverse is and only is that assuming we live in a multiverse allows us to explain a life-conducive universe, that doesn't seem evidentially very impressive as evidence for a multiverse. Similarly, if we think that there is a created God, if our reasons for thinking there's a created God are and only are that a created God explains the existence of life, that again doesn't seem to move us forward epistemically from just the direct posit that the universe is life-conducive. Now, you can see how that could go otherwise. If you thought there was antecedently rather a lot of evidence for the existence of God, then you're probably not desperately bothered or worried by the life conduciveness thing, because again, you've got an antecedently justified claim that you can use to ground it. If, like me, you think the antecedent evidential case for God is extremely weak, conversely, you're not going to be at all moved by that. And in a multiversal framework, if you only think that there's a multiverse on the grounds that you think it's necessary to explain life conduciveness, that looks evidentially pretty weak. If you think you've got a bunch of other reasons coming out from other bits of your theory to think there are multiverses, then evidentially it starts to look an awful lot more reasonable to say, well, given I already had quite antecedently good grounds for thinking there was a multiverse, then I don't find it terribly surprising that there's life conduciveness, and indeed I might regard life conduciveness as another, evidential brick to the pile of why I think there's a good case here. Okay, I think that's all I wanted to say.
Thank you very much. Okay, open to the floor.
Thank you, Simon Saunders. I have perhaps two remarks, or even a third, if you'll be tolerant. Just one remark on Shelley's classification. I would put the question, psi in what representation? What is psi on the psi is nothing view? I think you have configuration space in mind, so this is sort of rather precisification of what you mean by psi. And my own sense is, when you say to Jim that a decoherent history is not the history of the quantum state, fine, but the superposition of all the decoherent histories is the Heisenberg picture quantum state. Anyway, so for me, Everettian quantum theory, if you insist on your classification, is more in the middle, because I think it has structure, and in giving that structure, defining that structure, there's a lot of work involved in that, and I don't think that's just the sort of the psi configuration space, and that's the end of the story. Okay, so that's just a comment. I think the more substantive thing I want to say about what's been going on this morning, I mean, Jim says, the return of the observer, and I do understand the push that one, or the pull perhaps, of some of the scenarios that arise with especially eternal inflation. It seems in a very, very large universe there's going to be doppelgangers and so forth, and then it becomes meaningful and perhaps important to ask the question, what is the probability that I will see this first-person perspective? But I really want to pose the question, are we forced to this by physics? Can we not, in physics, resist this pull towards the first-person question? Can we not instead pose the question, what is the probability that such and such a physical system will be correlated with such and such another physical system, where the first named physical system is perhaps something like a biological agent, but physically characterized? So as long as you sort of fairly relentlessly stick to that way of posing and framing probabilistic questions about what theories predict and so forth, I think one might well avoid altogether the question of, well, how many doppelgangers do I have and what sort of a measure do I put upon them? Is this? Hello? Oh, it says right, it's still working. And my question to most of those who gave talks this morning that did buy into the first-person perspective and questions about the first-person perspective as being somehow forced upon us, Can you give me any evidence for that? Because, look, if the evidence for the need to consider the first-person perspective comes from concerns about selection effects, that human beings can only be found in certain epochs of the universe, that sort of consideration, I think that one already responds to those concerns by characterizing human observers in physicalistic terms and not going to the first-person perspective. I think you already deal with the known examples of selection effects and how we better pay attention to them from staying within the third-person perspective. And just on one other comment on Jim, saying that Copenhagen quantum mechanics was committed to the first-person perspective because of its use of the term or the concept of the observer. I talked to Jim about this, so just a quick comment. Bohr himself rarely, if ever, well, there were one or two occasions, talked of the observer. He talked about the classical measuring device. So this is really work of Heisenberg in the 50s and his coining the term Copenhagen. And Heisenberg, unlike Bohr, did fairly relentlessly insist on the role of the observer. It seems to me Bohrian quantum mechanics anyway does not go down the first-person perspective. And to seriously go down the first-person perspective in quantum mechanics may well bring in many of the problems that we are seeing in the measure problem, even though we have the Born rule. Anyway, so the challenge is, why do we need the first-person perspective?
I thought they were going to respond.
I think Jim should
I
respond.
think we must get several and then respond.
Yeah, play it by ear, I think. Doesn't need to be a rigid rule.
Jim Hartle, thank you for that correction, Simon. I will make these remarks of Bohr about Bohr in the proceedings, that I did say that it was a revisionist history. It was a revisionist history, but I want to address, I think, both of these comments, and also to some extent David's first comment and what Simon just said. One of the things we have in quantum mechanics is the opportunity to coarse grain over things that are irrelevant for us. In a very large universe, right, as I illustrated, paradoxically, maybe, it becomes easier to do that because the first person and third person probabilities coincide. So the way we actually do our calculations is to coarse grain down to one Hubble volume, our Hubble volume, right, and then do the straightforward third person calculations, which now, because of ordinary physics, are contingent only on events in our past light cone and have no dependence on the future. So if you don't have to compute the entire situation for the universe, and as several people have stressed, it's ambiguous, right? When we tried to compute it, it depended on how you took the limits. But if you agree on on what we mean by coarse graining, to focus on one Hubble volume, ours, then the calculation is both simplified and more consistent with ordinary notions of causality. I do have a question to ask Shelley. Unfortunately, you gave me the microphone. These various views, 1, 2, 3, and 4, right? Are there any experimental consequences of taking one or the other? If so, why do we worry? If not, rather, why do we?
I would say there are no experimental consequences which distinguish any of the theories here except the thing I put in parentheses.
Careful.
Except the thing I put. GRW. And that's why probably that's connected with the fact that it is in parentheses. So why should we care about it if there's no experiment, if there are no experimental consequences which...
Evidence that people care passionately about.
Why what?
The different points of view.
Why should they care passionately?
Oh, they do.
They do, but what's the question? Because, well, many of them are physicists. And physicists care about physical theories. And they want to understand what their physical theories say. All of these things say different things. They appeal in different ways to different people. This is exactly the sort of thing physicists should care about. They should, of course, be disturbed if there's no way to distinguish between these things experimentally. But actually, if you look at the people, some of the people up here, David in particular, David is utterly confident, despite the fact that there are no experimental distinctions, that his way is correct. So that doesn't bother him probably so much. And I would say the same with me. I would give little probability to the correctness, little credence to the correctness of Everett for a variety of reasons. But even if it were the case that we had two equally good, equally appealing, equally aesthetically nice theories which make exactly the same predictions, that could be the case, that could happen. I don't think anybody thinks it has happened yet. It could happen. If it happens, too bad for us. We won't be able to decide.
Could I add a little? Yeah, just to add a little bit. I mean, perhaps distinguish. There are things you might do to address the quantum measurement problem that involve playing around with the formalism of quantum mechanics, and there are things that don't. And of the things that play around with the formalism of quantum mechanics, it seems to be very much a live option that the developments of those frameworks lead to empirical predictions. The dynamical collapse theories do make empirical predictions that differ from quantum mechanics. As it is, there are experimental processes. You know, there are groups who've been playing at how to test some of those things. There are some takes on how to think about the bone mechanics that also lead to empirically different predictions. There has been work done to play around how to test these. If you look, on the other hand, at different ways of making sense of the formalism of quantum mechanics, then you're not going to have empirical predictions. Why care? Well, if you like, there's the high-minded answer and the pragmatic answer. And the high-minded answer is we're interested in science because we want to know what's going on and not simply because we want to make predictions. Predictions are a means to an end rather than the end in itself. The theory that fossils are dead dinosaurs makes the same predictions as the theory that fossils were placed on Earth so as to look exactly like dead dinosaurs but aren't dead dinosaurs. We still kind of care about the question of which is right. But more pragmatically, it does just seem to be a plain fact about the history of post-Second World War quantum mechanics that playing around with different ways of formalizing the theory have led to different frameworks, different formalisms, different sets of ideas. I'd include yours, Jim, very, very highly on that list, which have been motivated and inspired by the question of how I should think about and formalize and address the theory. And even if you don't want to think about that in a sort of realist way, which of these is true, it seems to be a highly helpful, effective strategy and approach to making better sense of quantum mechanics in ways that do lead to predictive consequences.
All of the discussion about EPR has led to fabulous experiments, and I think that's very important.
I would like to, George?
Khalil, can we carry on for 10 minutes, or must we finish now?
Yeah, because we have this bus will be waiting for us.
Sorry?
The coach will be waiting for us.
The call we were waiting. Yeah. So
George, I would like to answer to Simon's question. There was a specific question by Simon I would like to answer to.
Okay.
So the question is what pushes us to a first-person perspective, and I think there is a precise answer to that. And let me try very briefly to articulate it, even if it is subtle. The point is the following. If an electron in a double-slit experiment hits the screen, I believe it is a fact of the matter that there is a spot on the screen that the electron has arrived there. However, I also believe that quantum mechanics, up to contradictory experiments, is true. So I want a picture of the world where quantum mechanics is true. And quantum mechanics tells me that I can describe the electron and the screen as a quantum system, so put the screen in the Hilbert space to the tensor, and later on, make a measurement that detects interference effects between the electron having made a spot here and a spot here. Other people may say that no, that's a different expectation about measurable thing. But I think that quantum mechanics predict that. Therefore, there is a sense in which, with respect to me, I'm using the facts, with respect to me, the spot on the screen here or there is exactly as the particle having gone through here and there. So since not following Shelley, since I want to say that there's no meaning to the fact that the particle has gone through one or the other holes. In the same manner, with respect to me, there is no meaning of the existence of a spot on the screen here or there. Therefore, it is at the same time true, according to quantum theory, that there is a spot on the screen and that there is not a spot on the screen. And there is a way out from that. The quantum mechanics itself provides, I believe, that there is a spot on the screen with respect to the screen, and there is no spot on the screen with respect to me. Why? Because I interact with the system only later, and the fact of the matters are realized with respect to me only later. So this argument, for me, this is the core of relation quantum mechanics. This argument is what forbids me to take, to mix the first person and the third person, and somehow any perspective turns out always to be a first person. The only third person point of view is just nothing happens.
We can carry on for another 5 minutes.
This could be a long discussion.
I know. That's the core of the, yeah.
Yeah, this is sort of for Shelley. I mean, you told us that you wanted us to adopt this classification of what these meanings of the wave function were, and, you know, everything, something, nothing. But
Or
for
none
me,
of the above.
For me, I heard that this was equivalent to that you're supposed to adopt the classification of the wave function for psi of elephant, psi of giraffe, and psi of earthworm, or some other random set of words. It doesn't really mean, the words that you're using really don't mean anything to me, and to ask that everybody adopt that classification seems perverse. Now, that people make clear what it is that they're talking about is, of course, a good thing. And that, I think, was part of what your message that you were trying to give. But I don't think that this classification you've given is something that is going to make it clear to anyone.
Perfect. But see, I would say it's good to have an example here of none of the above. And then if you were giving, but I would say if you were presenting or writing a paper on your own version of quantum mechanics, you should elaborate on exactly what you said there about why these questions seem meaningless, and that would be actually, I would find that it's absolutely essential to understand what you have in mind when you say these questions about the most basic object in quantum theory. You would think these are sort of the most straightforward questions. It would be very important for you to explain why they mean nothing to you.
I wanted to focus on Carlos' position. Two things, two questions. The first question is, in this last description that you said of the wave function, the relative wave function, one according to which there is a spot on the screen and at a particular point, and one other one in which you have the wave function. What is the mathematical structure that will avoid conflicting conclusions that you may arrive from using different points of view? Do we want to say, I will forbid any argument that leads me to some contradictory position, or there would be a mathematical structure in your theory that ensures that no such contradictions are possible? That's the first question. And the second question is, you were saying quantum mechanics is not about the wave function, it's about facts. What is the mathematical description of these facts? How do we get the mathematics, how I characterize mathematically the facts that we want to talk about?
So I respond very rapidly. The correct mathematics, as far as we know, in my opinion, is the one we learn in books of quantum mechanics. So of course I use the wave function, but I also use the Hamilton-Jacobi function, I use the Lagrangian, so this is... Exactly. So the fact is that the electron, that this arm of mine is here now, that you are talking to me, that there is a photon hitting me, that is, these are the facts. Sorry?
It needs to be classical description.
No, I think these are the facts, and they are described in classical physics by point in phase space, in quantum physics by eigenvalues of operators. Yeah, these are the mathematical description. In fact, if you read Dirac's book of quantum mechanics, he starts by using states which are eigenstates of operators, and there are those states which are have if you want to be a realist, it is there that you have to hang your interpretation to. So in my opinion, a lot of views of quantum mechanics just forget that to use quantum mechanics is not enough to have a Schrödinger equation. You have to state what are your self-adjoint operators, and the spectra of the self-adjoint operator represent what can happen, and which one happen is given by the probability rule.
Then the issue is how the description of your system tells you which, not the description of you talking outside the theory that I am interested in this or that, but how your full description of your system in terms of quantum mechanical language tells you how to select the operator that you should use to select the path.
I agree. I fully agree. And the full description, if you take Messiaen, say what is a quantum theory, it is not, very strongly, it is not a state with a Hamiltonian. It is a state with a Hamiltonian and algebra operators. Unless you say what is the algebra operator, you have no theory. Because wait,
you have to say which one.
you have to say which one is the algebra, exactly.
I'll keep this short, I promise, Carlo. Cormac O'Rafferty from Waterford Institute of Technology in Ireland. I think the classification is extremely useful. It's a very useful list. But as usual, I'm just a little bit disappointed that nobody ever asks where Schrödinger himself fits in. He didn't just write down a wave equation. He spent 10 years sitting in Dublin writing about his interpretation of the wave function and what it meant. And when you ask that question, and I think Einstein fits into this category, you'll find it's actually quite difficult. I know Carlo would probably be tempted to put it in category 3, but actually they saw it not just as a mathematical tool, but as you know, as an incomplete mathematical description of reality. So I would say both Schrödinger and Einstein would add a 4th category there. Now, you could make an argument and say, yes, but Bell experiments, et cetera, would invalidate, and other people would say, no, there's loopholes. But I mean, to ignore all that early work, it always seems to me to be, there's a huge amount of discussion on this very topic in those papers that never gets referred to, and I think it's a great pity.
Schrödinger, I think, was very torn about the status of the wave function. So you're probably not going to find over his life, or even over a year of his life, a consistent story. He certainly wanted the wave function to be everything. People thought he thought all is wave. He certainly very well recognized the difficulty of that. That's why he came up with Schrödinger's cat. I think he never settled down to a view he was comfortable with.
I think let me advertise. There's a very nice paper by Shelley and a bunch of co-workers on exactly this question of Schrödinger's interpretation of the wave function.
Okay, can you please thank the panel for that discussion?